Okay. So now we'll have the second hands-on session of the day, entitled of Vessel Detection by Mr. Kristian Sørensen. And Kristian earned his master's in Earth and Space Physics and Engineering from the National Space Institute of Denmark in 2021, with a specialization on Earth observation. Following his master's, he pursued a PhD at DTU Security, from where he worked to enhance maritime domain awareness and surveillance through the integration of satellite data and AI. His academic journey also included research in Canada, Korea, and Norway. Currently, he is channeling his expertise into a startup venture. His research primarily revolves around the fusion of satellite data, including synthetic aperture radar image and AIS data for maritime surveillance, and the development of predictive models, for example, trajectories. Thank you very much, Kristian.
Oh, thank you. Great. Of course, everything's amazing. So yesterday, Ms. Eugenia Nunes gave us a really good presentation about a bunch of stuff, among them the Sustainable Development Goals. And here she mentioned quite a few of them, among them number 16 on ocean pollution and fishing zones and other things. And she said that this is one of the goals where EO can be used the most. She also mentioned SDG 16 on peace and injustice and said this is one of the ones where it's currently being used the least. At least that's what my takeaway from her presentation. What types of things can we then solve within these goals? Well, first and foremost, we have illegal fishing. And there is quite a lot of it. And according to some sources, it's up to 19% of all illegal, unreported, and unregulated fishing is actually illegal. So that's quite a lot, and that is estimated to be as much as up to 26 million tons every year. That's a big issue for number 14, life below water, but also number 16, peace and injustice, also our economy. And I think it was last year the UN signed a historical deal, will some say, the so-called 30 by 30 deal, where they said that they would like to protect 30% of all international waters by 2030 in so-called marine protected areas. Here, different things are legal, some of them fishing, some of them diving is illegal. And in order to protect these areas, you need to monitor them, like the ones you have here near the Azores. I hope you can see. I think everyone here and online remembers the Nord Stream incident in September 2022, where someone blew up the Nord Stream pipelines, and this caused a lot of issues for life below water, but also the way we now and then perceive the political landscape. So therefore it did a lot for injustice. But pipelines like these are not the only critical infrastructure at sea that we are interested in monitoring. We also have wind farms, or like these communication cables. These near the Azores, there are a bunch of communication cables. Even if we zoom out, we see there are way more of them. And these are of course used for communication, internet and all of that. If they are cut, we lose internet. Believe it or not, this actually happens once in a while, especially I know near the Faroe Islands. It happens quite often by accident. We have also seen cases where it has happened, what we believe, not by accident. In particular for the people in the room here, one relevant case is the one that goes from Norway to Svalbard, where these communication cables were cut. In Svalbard, we have a lot of the ground stations for downlinking satellite data. So if these cables are cut, we lose satellite data. So it's quite good to actually monitor these and figure out what is going on near them. And generally speaking, we are also just interested in monitoring huge areas on the ocean, not only for weather forecast, but also for security-related reasons. Number 16, peace and justice. All coastal states, they have full sovereignty over their waters, so that means that they need to monitor them, keep them safe and secure. If there are oil spill, they need to remove it. If there are someone in trouble, they need to perform some sort of search and rescue operations. Personally, for me, I'm from Denmark. In Denmark, we need to also monitor the waters around Greenland, which is quite a lot of area to monitor. Up there, we do not have coastal radars or other things to monitor from land. We don't have planes, we don't have people on land, we don't have drones. But we still need to monitor the area. And this leads me to my talk and hands-on session today, where we'll be working on maritime surveillance with satellites and artificial intelligence. And this presentation will be roughly 20-30 minutes on presentation, and then we'll do a little bit of hands-on. Simply put, I find ships. I figure out what they are, who they are, what they're doing, what they're going to do in the future. But more interesting, I find some ships that are doing something somewhere that they're not supposed to do, meaning illegal stuff. That could be illegal fishing. That could be general surveillance over maritime protected areas or in huge areas as near Greenland, or specific monitoring near critical infrastructure. But generally speaking, when you do maritime surveillance, there are different ways to do it and different ways you should think about it. And one of the ways is to do historical analysis. Here you want to say something about what has been going on, what is the quantity of the problem, like what I said in the beginning with all of this illegal fishing. This is a historical analysis. You can also figure out what is the quantity of oil spills or whatnot. When you do historical analysis, you are allowed to use many types of data sources and combine them into one result, or you're allowed to use big-ass models and all of these things. One case is the one you see here, where I've taken a plot from a paper that came out a few days ago in Nature about fishing and general vessel activity. And here they analyze how many of the fishing vessels actually reported what they did. And they found that, for instance, near Africa, it's only 22%. Near Europe, it's 60%. So there are a lot of fishing that is going on that is not being publicly reported, at least. And they did a lot of other analysis as well. And then the other way to do maritime surveillance is to do near real-time analysis. Here, you need to consider your objective, and depending on your objective, you're not allowed to use the same data sources or the same models as you do for historical analysis. For historical analysis, you can take one satellite image, and then wait for a few hours for another satellite image, and then you can combine these results to make some sort of nice analysis. That could be you take one satellite image, and then a while later you get some sort of image from radiometry, and then you combine these results. You cannot do that with near real-time analysis. You can, but that should not be the first thing you do. Likewise, you cannot use the same types of models. For the rest of this presentation, I will talk about some general data sources for maritime surveillance, and then I would actually show you some examples of objects. And hopefully that makes sense when we reach that point why I want to show you objects on the ocean. Let's see. And then we go to the workshop. There is no methodology or theory here, because I hope that the workshop, the notebooks, are kind of self-explanatory. And as you probably already noticed, this presentation is a bit different from most of the others, because they they focused on a tool set, where here I'm focusing on like a very specific problem. Yes, and we'll focus on near real-time analysis. Of course, one of the most well-used data sources for doing maritime surveillance is something that is called automatic identification system data, or just AIS data. And a lot of the times when I say I'm finding vessels, people just say, why don't you go on to maritime traffic and find them there? I can do that, yes. It's not always that good. And for those of you that do not know, AIS data is just a type of data that most ships should always send out, depending on what type of ship they are. They have information, timestamp, what they're doing, where they're going to be in the future, and all of these different things. So just by monitoring this, you know a lot about what is going on the oceans, actually. But they are not good for monitoring illegal activity. And why is that? Well, AIS can be turned off. Simply speaking, you go onto a vessel and you just turn it off, and now you're not emitting the data anymore. Guess what? A lot of the people that are doing illegal stuff turn it off. Sometimes the data that is received by the transmitter is, simply speaking, not being received from this receiver for different reasons. Sometimes the receiver is not near. Sometimes the signal is simply just not powerful enough, so to say. They can be jammed, it can be spoofed, they can customize their own route such that they say to the AIS data that they're sailing this way, but actually they're sailing there. So the objective in near real-time monitoring is to find these vessels. Yep. So what types of data can you use to do that? Well, you can use free images, freely available satellite images. Some of the most well-used ones are Sentinel-1, Sentinel-2, and generally speaking, SAR data and optical data from free constellations. And this should be the main data source, because you want to do surveillance on large areas all the time. You cannot afford, unless you are the American government, to always pay for really expensive satellite data. So you're depending on the free data. And that is like something that always should be running, and then you're detecting something on the free data all the time. And then when you find something of interest, whatever that might be, then you can pay for some commercial images and figure out what is actually going on down there. They can be higher resolution, they can be a different type, whatever. You can also use other types of satellite data, of course. We have the AIS, we have something similar, VMS, NRD. That is, even though a ship, especially in the Arctic where I'm looking at, a ship, even though it's not transmitting AIS data, it is still very interested in knowing whether or not there is an iceberg somewhere. And therefore they use navigational radars. Now these emit signals that you can actually receive from the satellite. So a lot of ships are still sending out some sort of information that you can find. Yeah, and then of course you also use other data sources. Coastal radars if you have them, and other types. The thought here is that you use as much data as possible. You can't afford to focus on one specific sensor, on one specific satellite, or even one general type of sensors. If you want to do near real-time analysis, you need to combine and do a lot of data fusion. The two, I think, most well-known sources is probably the Sentinel-2 optical data and the Sentinel-1 SAR data. Here I took 1 month worth of images near this island, and it should clearly illustrate some of the issues with optical data. If you want to do near real-time analysis and you would like to trust your data, then generally speaking, optical is not the best. You still use it whenever it's available, but it should never be the main source. On the other hand, SAR data can pretty much always be used. Of course, there are some advantages and disadvantages. The clear advantage from the SAR images is that they can look through clouds when you are here. Up in Greenland, it's dark for extended periods of the year, so it's also pretty neat that it's not dependent on the sun. But there are also some disadvantages. They are more complex to analyze, and even if you just look at it here, you can see the water is sometimes very bright, sometimes dark, and that adds to the complexity. This is due to the scattering of the surface of the water. So it's a bit more complex to analyze. Generally, they have poor resolution, but if you buy commercial data, you can still get really high spatial resolution, but the images are not as good in other sense then. Okay. Some SAR images have very many ships in them. This one have like, I think 500-600. I've seen up to 1,000. If you were to find them by hand, it would take a long time. Trust me, I've made a data set where I did that. It took many hours for one image. It is what it is. Some images have very few images. So ships. Many different types of SAR satellites exist, and they all have their, their own purpose and rights. So here we see some different resolutions from different satellites. 4 different resolutions from 3 satellites. Some have a very high resolution, some not as high resolution. But if you want a high resolution, you cannot see a very large footprint. So if you have a SAR satellite with 1 meter resolution, you're probably looking at 20 kilometers, whereas the one down here looks at 250 kilometers. So again, it's a trade-off. For the rest of this presentation and in your workshop as well, we'll be using data from the Sentinel-1 satellite. This is also the satellite that this paper from Nature used. All right. So now we have seen some SAR images. And that leads me to why I want to show some examples of objects on the ocean. Because a SAR image is, due to the way that SAR images are being created, like you get very, very bright signatures from scatters on the ocean. And I have seen both in research but also in industry that the general idea is, okay, if you find some sort of object on the ocean using SAR data, and this object is moving, then it is a ship. And I'm now showing you some examples just to show that that is not the case. So here is our first object. And I mean, of course, a lot of you have not seen SAR images before, but let me just ask you, would you believe this to be a ship? No. Okay, this is actually a ship. And this is one of the best cases of a ship. Like this is the best you can get. Especially if you want to do derived analysis. What about this one? I mean, you can't be right, but let's just guess anyways. Ship? This is a skerry. No, not necessarily. No. What you will see, if you are lucky, is an offset, depending on its orientation, and that is normally what you would use. If you have higher resolution and different frequency, then you can see the wake. Like if you have X-band, high resolution, you see a wake. This is a skerry. Many places in the world, skerries are well mapped using landmasks. They are not near Greenland. So then you're like, okay, can we do change detection? Yeah, you can. But if you just analyze the picture you had just before, then you would actually see that this moves because of the tidal effects. So you can't even do that. What about this one?
Platform?
Not a platform. This is an ambiguity. So it is, technically speaking, a ship. It's just a copy of the real ship. So can you see this really bright spot on the top? That is the real ship. And then these two thingies down there are copies of the same ship. due to, simply speaking, you can't have a perfect antenna. There are also side lobes, and if it's a really, really bright ship, the signal can enter the side lobe, and this is what we see here. So copies of the real ship. This is very difficult to say if you do not have the general context of the image. So imagine if I just look at this small subset, then I would be inclined to say this is actually a ship. Especially if I do, let's say, change detection, because there's definitely not a stationary platform there. What about this one? Some of you would definitely know this one. This is also a ship. And this is one of the ones that I'm easiest to see, because this, if you know about SAR data, this is a corner reflector, and it makes it so easy to say that something is going on there. That's a ship. This cannot be a skerry, for instance. This one, a bit more difficult. It's an iceberg near Greenland, and here you can actually see quite a few icebergs near. And then I'll just, okay, let's take this one then. Not a ship either. This is also an ambiguity, but a different type. Here, if you do change detection, you would actually be able to see this, because this will show up every 12 days in the same image. But if you take the image just before, just after, it would be gone, and then you'd probably say this is a ship. This one, any guesses? That is a ship, and that is a ship near icebergs. So if you look over there, the dot is like kind of in the middle below. And that we only know because of AIS data. And that was spot on right there, so we know exactly what ship that is. But if you just look at the signature, it'll look very similar to some of the other dots. And that's because, believe it or not, icebergs and ships look very similar up in the Arctic. This one, just a classic natural ocean structure. And that is, as you saw in this video I showed you, sometimes there are very bright structures in the ocean, sometimes they're dark, sometimes these bright structures actually also look like ships. But the thing is, we still use SAR data even though it's so messed up, because they can look through clouds and we can use them all the time. It is what it is. Okay. Yes. And then we are going to the workshop. So generally speaking, what you do is you get some sort of data, you apply some sort of model, AI, machine learning, a student assistant, whatever, and then you detect ships. And then after you have found your ships, you can then make some sort of derived analysis. You can estimate the ship type, the ship speed, the ship direction. Sometimes you have a 180 ambiguity, sometimes you do not. You can, in some cases, not with SAR data yet, actually estimate the specific ship identity. You can estimate, is it currently doing some sort of military activity? Is it legal activity? What is its future trajectory? And all of these things. But today, I will provide some data to you, and then in the workshop, we will have some models, and then we'll just detect ships. Great. Let's see. So the workshop and data should be available online. The notebooks are available online on the JuliaEO here. It's the vessel detection one. If you want to, during the workshop, I will create a model. If you want to train the same type of model, you would also need to download some data from the Google Drive, but you do not need to do it right now, because I added a model already that we can use for the later notebooks. Yep.
Can I ask one separate question?
Of course.
So, in these examples, we basically try to identify whether it's a ship or not based on a single picture. I believe in practice you also include some kind of like previous satellite pictures, or like basically the time dimension. And how much does that help, and how
see, this is then going back to one of the very first slides I made where I said you need to figure out what is your objective. Now I'll give you two extremes, and then like whatever you might do is probably somewhere in between. One extreme is the historical analysis, where you can add everything you want to. Everything. You can map everything out that should be there, and then you can just make change detection based on that. You can add the time dimension. If it's a specific time of the year, there are probably no icebergs. You can analyze these ambiguities that happen every 12 days, all of that. No issue. Then the other extreme scenario is that you want to, as someone are trying to do right now, you want to do onboard computing on the satellite. Because as it is right now, we actually do not have a lot of data on the ocean. Because simply speaking, it's too power demanding to take images all over and send it down, because if you take 100 images out in the middle of the Atlantic, you see 2 ships. So people just choose not to do it. They try to solve this with onboard computing, where they put the model on the satellite and only send down the subsets where there are ships. In this case, you can add none of that. It's too power demanding, and the model will be too big, and it'll take too much time. And then we have like a spot where definitely you can add historical analysis. You can add. It's very easy to add something that you can put in as input into your model, such as the time dimension. That is very easy. Latitude, longitude, very easy. Putting a landmask into your model is already a bit demanding. So it depends on your need, and especially what you want to. But yes, you can. And it does improve, in some cases, a lot, especially in Greenland. To add these things to your model improves it quite a lot, especially due to icebergs. In my project, we are working with one of Spire's resellers, and so the data is from Spire's satellites, and then so we got it. We got it because it's part of the project that I made at my university with a company called Gatehouse Maritime, and they are a reseller of AIS data. And that's also here. I said a ship ID. Using the AIS data, imagine if you know where all ships in the world are, except the ones that are doing illegal operations, and then you find a ship, and that could only be one of 5 ships from your database, and you know where the other 4 are, then you can say, okay, it's probably that one. Yeah. This is one of the analysis that Gatehouse is doing. Yeah. Yes, so if you have downloaded the workshop, you should have 4 notebooks like this. There is also a data folder. Here there is a small test image from the Sentinel-1 satellite that you can open. On the Google Drive, I have a full Sentinel-1 image if you want to. And the package is, I wouldn't call it either a package or a project, but you can download it on on GitHub here. We have 4 notebooks. In the first notebook, I show how to download data from the Copernicus service in Julia. In the second, we will create a very, very simple deep learning classification method. In this method, we will take these small subsets. As I showed you just before, you can have a subset and then you have something. Is it a ship? Is it not a ship? In the second notebook, we'll train a very simple model to classify whether or not it's a ship, or in this case, an iceberg. We'll go to the data later. In the third notebook, we will then use this trained model to find objects on an image and then classify whether or not it's a ship or not. In this case, actually a ship or iceberg, but I'll come back to that. And then in the final notebook, we'll use another model, a so-called one-stage ship detector that takes an image and immediately say there is a ship, there is a ship, and otherwise it'll do nothing, say nothing for the rest of it. We'll go to it. Okay. So some of the notebooks I will just go through up here, and then you can work on them later, because for instance in this notebook you can download a Sentinel-1 image. It is not wise if all of you start downloading a Sentinel-1 image right now, so I'll just go through it. And then likewise in the second notebook, I assume you have the data set from the Google Drive. If you do not, just look up here and then you can do it later. In the third and the fourth notebook, I have provided the models in this folder that we'll be using, so you can still follow along and actually do the stuff in the third and the fourth notebook. Great. Let's see. In this notebook,
Can you read the text?
yes, I can. Another thing to note is that during the past few days we have seen some examples of really good Julia packages, and yesterday we even got an introduction to how you should make a package. This works. I made it specifically for this workshop, so bear with me. And if I should improve it, I'll most definitely use that. Anyhow, so in this notebook, you can just download data, and I actually want to just skip this one initially and then tell you to look at it later. But the reason why I then wanted to go through it anyways is because that I heard that there was someone here that early on tried to download data from Copernicus and Julia, but had issues with it. And that makes a whole lot of sense, because a year ago it was very, very difficult. But now it's very simple because of this new service that is called the Copernicus Dataspace. A new service that Copernicus made in November last year. So it's very new. And using it, it's very simple to write APIs or whatnot to download the data. So if you tried earlier to download data from Copernicus and you failed, I just encourage you to try again. And therefore I just want to show it and see how easy it is. There we have result detection. Okay. Here, what we do is we start by asking for some, getting the metadata. Even bigger, of course I can. Damn. Okay. Yeah, so we start by getting some metadata to figure out what exactly we want to download, because sometimes, let's say in this case I'm doing Sentinel-1, but imagine if we did it for Sentinel-2, you would like to know if there are any clouds in the image, so it's pretty neat to download the metadata and filter from it. And we can even illustrate the image before we download it. Here I simply define some parameters, a start time, end time, the satellite, and then I illustrate like just the second image in this data frame to look at it, and then you can download it. And I've downloaded this, and I created the small subsets that is then in the folder. So this is actually the image that we, well, part of this image we'll find ships in later. Again, this was just to show people that have failed downloading Sentinel data earlier that they should try again. Great, now for the real notebooks. Can you still see it? Okay, great. Great. So in this second notebook, we'll make a ship binary classification. In the notebook, there is some initial theory that you can read if you want to about some binary classification and other stuff. And then we are including the data. We are making the model using flux in Julia, and then we are finding a threshold to determine whether or not we believe that the subset to be a specific object. So, I will not go through the theory. You are welcome to do so yourself. I'll just go straight to the dataset. Because if you want to make a model that should be able to take a small subset and say, this is a ship, this is not a ship, or this is a ship, this is ambiguity, this is scary, then you need a whole lot of individual samples, right, from all of these different classes. The data set you have here will only have 2 classes, and therefore I already know that the model that we'll create will be very bad. But the idea is there. This data set I found online. It was created by a Canadian company called Seacore, where they hand-labeled a lot of images with either ships or icebergs. Nothing else. And then we'll take this, and then they made some transformations to the data. In particular, they made something that is called sigma naught calibration, which is, I think, not normal for other computer vision types of problems, but we'll now train a model on these subsets. Here, I'm using the train.json dataset that is online. If you don't have it, that's fine. You can do it later or just follow along up here. Oh yeah, that wasn't the other one. Great. All right. Give me a sec. Okay. So in this set, I have taken the data, I've loaded it, and I created a very simple function to just shuffle and split the data. No augmentation applied or anything. And what we have is then a little bit more than 1,000 training examples and 321 testing examples. Again, it's only either ships or icebergs. So this right here is an iceberg. If it's 1, it's an iceberg. If it's 0, it's a ship. And now we want to create a simple model to train whether or not it's ships or icebergs. Here, I've just, made a real simple function to create a model here. And in this case, we have a simple convolutional neural network that only use convolutional layers and other very simple layers. And then it ends up with just having the last dense layer. Yeah?
Good question. So you said you have just classes for ships and iceberg. What about what?
There are no other classes. Later on, I'll argue that this is very bad to do so, because you do not only, there is water on these subsets, but you need something with neither, you need something with different types of objects. But water is actually not the class that is needed, because this is just assuming that you have an object and trying to classify the object. So you will actually never have, when you use such a model here, you will never have a subset with nothing in it. But you might see subsets with other classes than ships or icebergs.
So is it classification for the whole image or per pixel?
This is a classification for these small subsets. Nothing else. In the last notebook, we'll use a model more in line with what you're probably thinking of on the whole image, but not this one. So a very standard way of doing ship classification, ship detection, and when I say standard way, I mean this paper from Nature in January this year and other papers that came out last year, they do ship detection in the following way. They may use whatever, they somehow detect objects using an object detector. After they have found an object, they take out the subset, which is what you see right here, and then they have a separate classifier where they classify, is this object that I have detected in the first step, is this a ship or an iceberg in this case? In other scenarios, they have more classes, but it still illustrates what a lot of people are doing, even the Nature paper from a few days ago. In the last notebook, we'll use a type of one-stage object detector that works in the full image, that has very many different, is trained on the full image. Yeah. But this is the way that a lot of people are still doing it. So people that are working with deep learning, they're probably thinking, why are you doing it like this? Because people are doing it like this. And I'm just showing you one way of doing it. Does this make sense, kind of?
Just a comment, there are different setups, right? So as explaining, there's detection, classification, and segmentation. These are three different machine learning processes. So he's trying to do detection. Someone did the detection, he's doing classification. There's also segmentation where you get each piece. So
if you do detection, you should also, ideally, you should also take into account that it's not detection.
So when I do, I'll just go back to the introduction of the 4 notebooks again. And I'll I'll introduce them a bit better, I guess. In the 3rd notebook, we'll make a very classic object detector that especially people within the SAR community is using very often. Then we find objects. This object detector is not in any way saying if it's a ship or something else. It's just saying there's an object on the ocean. Due to this notion that you would assume that most bright objects on the ocean are actually ships, so this is what people started using back in the days. And then you would take these detected objects and you'll classify whether or not it's a ship or an iceberg. If you are in Greenland, you quite often assume that it's one of the two. But as we saw, there are actually also other false alarms, such as the ambiguities. In this notebook we're in right now, we'll build this classifier. So we will actually not consider detection. We'll only consider classification of this object into either ship or iceberg. Then in the last model, we'll load and use a so-called one-stage object detector. This detector has been trained, granted, not on very many examples, but I trained it on full images such that it also learned what water looks like and other classes. Yeah. Did that help clear up confusion? Some? Great. Great, so we made the model. And this last layer down here, we are simply saying, okay, whatever features we have, squeeze it into one, and then we are applying a function to just map this into a probability between 1 and 0. In this case, due to our data set, if it's 1, we believe it to be an iceberg. If it's 0, we believe it to be a ship. Again, this is a data set that was used in Greenland, where you assume that these are the 2 things that you have on the ocean. Great. We'll now define some hyperparameters for this model and a simple loss function, and we can then train our model. And I do not assume that people would sit here and train the full model, so I have done it here, where, let's just put it down here. I have trained the model for like half an hour. And here I've illustrated the accuracy where I assume that the threshold is 50%, meaning that if it's above 50, it's an iceberg, below it's a ship, but that is not the best threshold, but it's just illustrating what we have. So we see that at one point the accuracy keeps on increasing for the training data, and it doesn't increase for the validation data, and that's where we stop and save our model. This model from this training, where I have stopped it, where they are not divergent, is the one you have here, the classification model. We now want to find some sort of threshold where we would say if it's above this, it's an iceberg, if it's below, it's a ship. And we do that on the validation data. And then we see that there is some sort of threshold where they have the same recall, if that's what you want to have. And then you can just say, that is our threshold. I've done that. And you can now test your data. Here, we have trained the model to only be able to say whether or not it's a ship or an iceberg. And we have validated on the validation set. Now we want to test it on the testing set and see how good it is. I pick this threshold that I will be using, and then I just tell it to give me the accuracies. So this is actually not a very good, okay, yeah. So I trained this new model so that I'll get really bad results right here. But let's say I didn't run it again. You would get at this threshold, here, you would have some sort of a similar precision of 90% for both ships and icebergs. So in the next model, in the next notebook, we'll be using this threshold. That is the only thing we need from this notebook, actually. Great. So now to what we actually want to do. We want to detect ships, in this case, a Sentinel-1 SAR image. And we'll do this in this 2-stage ship detector. The first thing we'll do is to load the data, obviously, and unfortunately you can't load a Sentinel-1 image as it is right now in standard Julia and still have all of the metadata. If you can, and there's a package for this, someone please tell me. Yeah? You can load the TIFF file, but you would still want to have the metadata that is not necessarily in it.
It's not inside the file.
So the structure of the...
I think I loaded it once when setting up file.
The data looks like... Okay, okay. I would like to see it, definitely. That would be neat. I'll see later. Anyways, otherwise you can load it here. This is a small subset of the full image where, why is this so slow? Where you can see that we have a bunch of ships up here. Like I showed in the very first example of different examples, this is pretty much how the ships looks like up here as well. But you can also see that the values are very, very high. So depending on what you want to do, you are often normalizing these images differently. If you only want to detect ships, it is actually fine that they are that bright objects are very bright and everything else is dark. But if you also want to detect, let's say, icebergs or oil spills, you would change the distribution of the data. And that is also what this data set did. So as you can see, the histogram, yeah, okay. I'm applying some transformation that the data set also applied. And in this case, in particularly, we have converted to a linear and decibel scale. And this just means that we are changing the distributions. So now the image looks like this. And we can see that there are a bunch of ships in it indeed. And you're probably wondering why we have changed the distribution to go from -30 something to 10. That is a very standard way of changing the distribution of SAR data to make it Gaussian, pretty much. Great. So now we have our image up here. And then again, the first thing we would like to do is to detect objects. And in this case, we'll be using a rather standard way of detecting objects in SAR data. In fact, I have referenced a paper in this very notebook that is from last year that is using the same method, and also this paper from Nature this year also used a variant of this object detector. Just to say that this is still the one that is being used. Well, a variant of it, but nonetheless. And I have here in the theory, I have another notebook called C5 where I can read about it, but what it is doing is pretty much just to say, okay, for a certain region in the image, we'll figure out, okay, what is the mean intensity, so to say, and if the pixel in the very center has a much, much higher intensity, then it's an object. Very simple. And this is called a constant false alarm rate. You can read about it in this extra notebook. We'll be using this to just find objects. Again, whatever bright pixels you have in the image will be now detected. The classic constant false alarm rate will give roughly, in this case, 53 different objects. A one that is also using morphology will give us 11 different objects. These are highlighted here. This is then the first stage, the object detector. In other computer vision tasks, you also normally use more advanced machine learning for this step. But for SAR, you often use this one. Now, what we'll do now is to take this model that we trained in the in the second notebook, and we'll then apply it to some of these objects to see, okay, do you believe it's a ship? Here we have one of the objects. And this is very similar to the first example I showed you, I reckon. And that's because this is a very classic signature of a ship. We now just want to use our model on this example. And we are now normalizing the pixels to lie between 0 and 1, where they were from -30 to 0. And now we'll see what the model believes. Okay, so there is 0 There is a very, very small probability of this being an iceberg, is what the model is saying right now. And that is very similar to how a lot of people now are finding ships. I had some tasks during the notebook. A lot of them are where I want you to try to change some things. But at the very end here, I have some questions, and we already discussed some of them. Because, of course, there are very many drawbacks to this method. In this data set, we only had ships and icebergs. What happens if I give it an object that it hasn't seen before, such as these ghosts, these ambiguities that I showed in the example? Then it will most probably guess one of them on one of them with a rather high probability. And that is one of the big issues with this method. Yes. That leads me to the final workshop. In the final workshop, we will take the same image, but we will use another type of model. This model is a type of one-stage object detector that will, from the full image, say, okay, maybe I should actually just... It'll take the full image, and it'll divide it into regions that you, when you define your model, define. You can say that every region should be 4 pixels, 5 pixels, 10, 20, 30 pixels. Within each of these regions, you would want the model to, in one step, say, do you think there is an object or not? If you think there is an object, what object is it? If there is an object, what is the size of the object? So in this case, we have ships, a ship there, a ship there, a ship there. We have some cranes, ships. So the model should then say, okay, here we have a ship, a ship, a ship, a ship, a ship, a ship, so on and so forth. Over here we have no objects, and here we have cranes. Now what is then no object? Because if we just look here, of course there are objects. Well, everything that we have not labeled are considered no objects. So if we only label ships in these images, the crane would also be a no object. Whereas if we would label a pier, then a pier would have a separate color. After you have detected the objects, you will estimate its size. But as you see up here, then in this very big ship right here is in many different of these defined pixel sizes. Therefore, many different of these cells would say there is a ship. This is what you see here. So we end up with having several of these estimated sizes. You would then remove the extra ones, and you would end up with something that looks like this. So this is a model that takes one image, and the output will be this. Yes. Someone mentioned the wake earlier. Here we could see what it normally looks like, actually, very zoomed in. Believe it or not, the ship is actually here. And then it's just due to the SAP processing that it appears to be down here. But if you know about this and you can correlate for it, it's not an issue in your later processing. But for all intent and purposes, when you detect ships, you would estimate it to be here and not up here, because it's easier. Great. So now we would load the same Sentinel-1 image, the model, and the text ships with this model. This model was trained with some other transformations. For instance, here we are not doing this linear transformation that I used before. Otherwise, it's very similar. This is then the image. It looks very similar, but with different distributions, and that only depends on what you trained your model on. And this model was trained on images with these distributions. Great. Now we'll load our model. And if you want to, this model right here is in the so-called ONNX format, which is cross-platform. So you can use it in Julia, you could use it in Python, and in very many other languages. And it just works as is. And you can illustrate it online if you want to. In Notebook 2, we made a very simple network, so it was quite easy to just illustrate the different layers. This one is a bit too elaborate to show here, but you can take the model and you can illustrate it on this app if you want to. Up to you. Then we'll simply speaking we'll just find ships by using the model and the image. So now this model has found ships in the image. Here we didn't apply some sort of object detector before. We just gave the full image to the model, and it output this. And as you can see, there are very, very many bounding boxes, and you can see these probabilities are like on top of each other. And that is because I have not applied this so-called non-max suppression to go from this step to this. We could easily do so. And we also see that these scores here are around 80%. And if you are familiar with other, how can you say, examples where you apply some sort of model like this, they are often actually higher. But that's because this model, first and foremost, it's a simple model. It didn't use a whole lot of data to train it. And also the output is a combination of, okay, how sure are you that there is a ship? And how sure are you of this size of the ship? And if you have seen some of these SAR images, you can see that it's not always clear where the border is. And that also reduces this score. Yes. That was actually the introduction and walkthrough of the notebooks. I have made many tasks that I think you could do if you have the notebooks and you want to do it. You can also do something else with it. And otherwise, I'm actually already finished. But that's okay, I guess. I would recommend everyone to just work on these notebooks, look at these tasks I gave you, or drink coffee, or ask questions.
Just modify the SAR, as far as I know, it's not the The sensors of the side on the satellites are not turned on when they are over the ocean. Is that right?
That is that is in part correct, right? Yeah, and that is why
when they come close to the coast, is that they start acquiring data. I remember there was a problem, for instance, when people wanted to do inside data, because you need almost to ask
yeah.
to turn off the sensor to have data on the islands. Now it's a bit better. Last time for St. George rises, I looked at it, I could get a couple of them, but I only saw data around the islands. So it means large part of the ocean you don't have data for your account. That's right.
That is absolutely right. So there are depending on the satellite constellation, of course some people can say, okay, we want pictures from these areas, such as from Sentinel-1. There we have data from these areas near Greenland. So in all of the areas that I'm interested in, at least, we have data. But in the middle of the Atlantic Ocean, currently, there is not any data unless you know that there is something going on. Let's say that you know there is an oil spill, then they take pictures from this area. Otherwise, they do not. And that is because of the power budget and the downlink. But this picture is actually changing. This maritime picture is changing, not because of these historical analysis, but for near real-time analysis, there is this shift in the commercial scene where you can still get pictures in the middle of nowhere as long as you say you want pictures from that area. And you pay it.
And it's a lot.
Yeah.
It's not for
Yeah.
research.
No, it's not. It's definitely not for research. But I would say, at least for my case, these areas around Denmark, Faroe Islands and Greenland are well covered by Sentinel and RCM. Quite well. But in the middle of Atlantic, no, not unless you pay.
Okay, another one for curiosity, it's still about the waves. Those very high speed boats that Portuguese and Spanish know that transport very high valued goodies, but they travel very fast. They should leave a good wake. Do you see that?
Yes. Yeah, I see them, but I mean, we have wakes in 1 in 30 ships we find. It's in this ballpark. But that's also because we're not focusing on these small, high-speed moving ships. So, but yes, they have wakes, but not, as you saw, these ones did not.
I think some time ago, long time ago, I saw some advertisement or something, and where we had the SAR, amplitude data with the ship and a very nice wake. And I got the wrong idea that you see wakes everywhere.
It's also dependent on the specific SAR sensor.
Maybe I can also add a little bit. It's also when you have the SAR, it's also very much dependent on the direction of the waves relative to the sensor. So you can have, if the waves goes one direction, you can see it, and then if the boat turns 90 degrees, it's much harder.
So earlier, years ago, there was also a lot of research in only finding wakes, because if you find a wake, you assume that it belongs to a ship. But that was when people did these sorts of ship detection methods where you first find objects and then you estimate, is it a ship or not? Because here you only see this small subset. But in these other models where it's so-called one stage, you train it on full image. Inherently in the data, when you say there is a ship and there is a wake out of it, it is being used in the model. So wakes are still being used, but not all ships have wakes.
We work with some work with air center where we classify the data in satellite data.
Yeah.
And one of the big problems is that you sometimes have unbalanced much more pixels per photo.
Yeah.
then wave picture. And I'm wondering if you also encounter some issues that the class are not balanced, or what kind of approaches did you to avoid some.
The approach we took, simply speaking, it is unbalanced because we will never have as many of these azimuth ambiguities as we will have ships. But sometimes when people train these types of models, they do it on full images. And that leads to highly imbalance between the background and objects. Here we, simply speaking, just cut out a lot of the background. So there is at least a balance between objects and background, but not for the different classes. Yeah.
Thank you.
Hi. Is there any false positive issues because weather conditions, atmospheric conditions, like to detect oil spills?
For oil spills?
Yeah.
False positives for oil spills? Yes. Oil spills, for those of you, so ships are very, very bright on SAR images. Oil spills are very dark. And the only reason why they're dark is because in this video that I showed in the presentation, you could see that sometimes the image is dark, sometimes it's bright. That is due to pretty much just the waves and the scattering of the incident radiation. So if you have many waves, it's very bright. If the water is completely still, it's dark. What oil spill is doing is it's lying on the surface of the ocean and makes it so that there are less waves. That is what you observe in SAR data when you observe oil spills. So oil spills is just dark patches. Very many different things are creating dark patches on the ocean. But a lot of these things do not have the same structure. So if you talk about oil spills, we have large oil spills, we have very, very small oil spills. Very small oil spills can honestly look like very many different things. Large oil spills do not. So if you somehow make a model, if we actually see this, maybe if we see this image again, so I don't know. Oh, you can't see it. Down here, it's always dark when I look at it here. And that is because due to the geography of the land, it's always, the surface is always dark. If you do not make some sort of model that has these dark areas, then it will detect everything as dark against a bright ocean as oil spills. But simply, if you include those, it's actually not that difficult because oil has a very specific structure. Algae has the same type of structure, but they are often bright in pictures against a dark surface. So the most difficult thing is actually just to find, get information about where the oil spills are. Yeah. But I wouldn't use the same type of model. This one was making a bounding box. For oil spills, you would like to do segmentation.
Hi, Kristian. How do you differentiate the icebergs from the ships? Is just the shape or also the strength of the signal? One are more roundish, something, or less?
Yeah. So you can't use only the strength of the signal. So you are highly dependent on the conditions and the shape. But honestly,
I mean, sometimes visually we understand the difference between two different features.
Yeah.
And then we train models to try to replicate what we see.
Yeah.
But do you see that in the iceberg? Do you understand visually?
No.
Right.
Look,
so the model, so likely the model will also not.
This one right here is a ship. This one down here is an iceberg. This one up here, iceberg, iceberg, iceberg. Why do I say that? Honestly, I do not know. I just know that this one is the only one that had AIS data. And I also know that there are very, very few ships in these waters. It's very rare to have many ships in one of these images near Greenland. And that's why we, when I create my data set at least, say this is a ship. And then you can make some nice graphs that are saying, okay, how good is your accuracy according to the size of the ship? But honestly, if a ship is 20 meters, then it's almost impossible to differentiate between iceberg and ship. Even this one right here, this is the so-called side lobe, because of there is a very high wave that is being scattered from the object. If you are in most places in the world, you know almost for sure that they are man-made objects. Icebergs can make the same. So it is very difficult. Huh?
The optical signature of the iceberg, no? Before, of course, you are using the IES, so you know where they are.
Yeah.
So you can distinguish them between icebergs and the ships. But if you don't have that information, you are looking, for example, plastic. Do you understand what my question is? You can use the optical image first?
In Greenland, well, the places where you have icebergs, it's of course dark for parts of the year. When it's not dark and you do have optical images, it's cloudy between 60 and 80% of the time. So, yeah, it's, yeah. And if you are down here, I hope there are no icebergs.
Right.
Yeah. Yes. Perfect. Well done. That's it for me, I guess.